All right, so we talk about the very first class here, what is calculus? What are you studying? Calculus is a different kind of math. It's unlike the pre-calculus things that you've been doing. The concepts are anyways, but the foundation of calculus is what you've been studying the last little bit. So all these pre-calculus classes you've been doing have been leading you up to launch you into concepts that are new and exciting and different and solve different kinds of problems. So calculus is split up into two main branches: differential calculus and integral calculus. Differential calculus is where we're going to spend most of our time in Calc 30, differential calculus. We touch on integrals and integral calculus at the very, very end, okay? And for this introductory course, we've focused mainly on the differential side here. Now, you'll notice that this black graph is a strange, curve, and this red line is a straight line, and it's a tangent line to the curve near this point right here. Okay, so if I were to zoom in on this red line intersects the graph at one point in this general area right here. We're not considering this intersection or anything that may be over here, but at this point, this red line is called a tangent line. Okay, by definition, a tangent line only touches the graph at one point. So if I asked you to find the slope, okay, of the tangent line, the red tangent line, you wouldn't be able to do that given the information that you're given on the graph. Why? Who remembers what slope is? What's the definition for slope, or the formula for slope? Yes, thank you. Rise over run. That's great. Also can be expressed as delta y, that is the change in y values, divided by the change in x values. Rise over run. Also can be the difference in the y values, y2 minus y1, divided by x2 minus x1. Okay, now the problem is, of course, and we're going to spend a lot of time on this in section 1.1, we're going to talk deeply about this, but the problem here is that there's only one point that's given. So guess what? In order to calculate slope traditionally, we need 2 points. There's the first point, there are the coordinates for the second point. So with only 1 point, we cannot calculate the slope of this line. If this graph were some kind of motion of a particle, and this would be some kind of distance over here on the y-axis, and time, let's say, on the x-axis here, let's say seconds, then this slope of this line would represent meters per second or some kind of velocity. Now, the tangent line at this point would represent something called the instantaneous velocity of the particle at this one instant in time, this one value for the time here. So if we only have 1 point, we cannot use any of this to find slope. This is where calculus comes in. And this is where, again, we will start talking a lot about this in the first section, but the concept of limits come in. So right away, first of all, calculus can help us determine instantaneous rates of change. That's a huge part of what calculus does, which regular math is insufficient to do. Now, geometrically, you could do this. I know in Physics 30, you guys do lots of motion problems. When I was teaching Physics 30, we used to chuck stuff out the 4th floor window here, and we used to time their fall. We used to graph things, and then I would say, okay, how fast is it going? 1.65 seconds after we dropped it. You'd be like, how'd you do that? Well, if you graph everything and assume that it's a sort of a parabolic, graph, you could actually find the instantaneous rate of change of that object falling out the window geometrically. So you could draw an actual slope, a line that touches the graph that you drew at one point, and then find the slope of that line. And that's the instantaneous rate of change. And actually, when I was teaching physics and calculus at the same time, we did a combined little project. Okay. So that's one thing that calculus can solve, differential calculus, instantaneous rates of change. It can be speed, instantaneous speed. It can be anything. If you're talking about industry or business, right? How much money are we making at this point when I'm selling this much and all this sort of stuff? How much money am I actually making today? Or what's the trend? Is this going uphill or downhill? You take a snapshot of your business model. Is this going in the right direction? Well, if you knew what the instantaneous rate of change was of the variables you're considering, and it was a positive rate of change, you know that you're going in the right direction. If it's a negative instantaneous rate of change, you think, well, that's actually maybe going in the wrong direction. I might be going in the wrong direction. I might be losing money soon here. Once I, after a week or two, I might be actually losing money. So there's that stuff. Now, the integral calculus, one of the things that you can solve using integrals, first of all, integrals represent, one of the things they represent would be an area underneath a curve. So this little blue section here, blue section A, this would be area under a curve. Now, area is really easy to find if you have some kind of shape that you know the formula for. Like if it's a trapezoid, or if it's a triangle or a rectangle or a square, you can find the area pretty easily. But when one side, let's say, is a curve, it's not easy to find that area. So integrals help us to find areas under curves. Why would that be helpful? Well, let's say this is a velocity function, and this is time. You could find the area under there, okay? And that would, that would tell you, something. If it's a position versus time function, where are you at a certain time? Where are you at a certain time? And then you come back. The area might represent displacement, so how far you've traveled or something like that. If you have rates of change like how many people are leaving the store that you're running, and also a rate of change of how many people are coming in the store, those rates are different. If you combine those functions and integrate, that area might represent, the total number of people you have at any point. Stuff like that. So you could extend this type of math to solve problems that are pretty out there, or problems that wouldn't easily be solved using regular methods. Okay? Yeah, question?
So does integral also have to do with rates of change?
Yes. Rates of change and integrals are related. The derivative is what differential calculus is about, and the integral, which is what integral calculus is about, they are related. And we'll talk about that at the very end of the course, actually. The very end of the course, the fundamental theorem of calculus talks about how they're related. But yeah, you'll find out before the end, but yes, they are related. Yes, they are related, okay? So calculus is really cool in a sense that you're going to be learning things that you've never learned before. You think about, grades 5, let's say, to grade 11 last year, okay? So you were working on multiplying, dividing, adding, subtracting. Oh, you added some transcendental functions in there, sine, cos. Oh, so maybe some logarithms, stuff like that. But you've been coming back to all of the same sort of types of math things, right? You've just been building on those, building. Well, now you get to take that package, and now you get to move on to calculus, and a lot of these concepts never heard before. So it's pretty exciting. I like calculus. I love teaching grade 12 calculus here, so this is going to be a great course. Okay, so that's just an overall big picture, differential integral, rates of change, areas under curves, things like that. Those are the two things, and we're going to use those concepts to solve all sorts of types of problems. Some of them you'll find interesting, some of them you might not. I don't know. But anyways, all right, so you do not have this in front of you. Just take a look at this. You don't have to copy any of this down, okay? But the skills that you will need for calculus. Okay. Now, I did recommend that some of you watch some of the videos before you came here today, just refreshing yourselves on factoring and working with different algebraic things. Some of you watched them, some of you maybe didn't. But if you have time this weekend, you might want to watch something on factoring. We're going to practice that a little bit today. But for example, factoring is probably one of the most important things that you need to know how to do in all of math. So factoring is really important. All of these algebra components like exponents, rationalizing, simplifying rational expressions, solving simultaneous equations, systems of equations right here. Also graphing, knowing about lines. Conic sections, it's not really in our high school curriculum much anymore, so you don't have to worry too much about that. We'll deal with that as it comes. Circle, conic section, circle functions would be something that we will talk about. Functions, we're going to spend a lot of time reviewing functions and using functions. Functions are pretty important to understand. We'll go over those today. Basic shapes and formations, transformations. We spent a lot of time in transformations in pre-calculus 30. Tests for symmetry. We haven't talked a lot about this, but this is pretty easy. We'll get into this this course. So geometry, there's Pythagorean theorem, areas, area formulas, volume formulas, all that sort of stuff. Logs and exponents, trigonometry, sine, cos, tan. And now limits. So limits, this is something that we're going to focus on in calculus. This is something that you haven't been exposed to in pre-calculus. The concept, though, is something that I have brought into some of the pre-calculus concepts that we've learned. For example, if you take a look at a graph, right, some kind of graph like this, and the graph looks something like this, I have asked you, if as the x values increase and start to approach infinity, what does this graph seem to do, right? So that kind of wording is sort of the beginning, the launch point for understanding limits. So if you think about it, as x gets larger, the value of x would approach some very large number, or let's say it approaches infinity. Let's say infinity is a concept that is the largest number possible. Let's just say that's what we conceive it to be. What does this graph do? Well, what we could notice is that this graph gets closer and closer and closer to, I'm not drawing it very well, but gets closer and closer to the x-axis here, which is y equals 0. So you might say, as x approaches infinity, the graph tends to approach the value of 0. And that is the concept of a limit. So we've actually talked a little bit about this, but we haven't used the actual term limit. And so that's what we're going to start with. So if you don't know what limits are, don't worry about that. That's what we're going to kind of launch off into. All right, I'm going to keep going here. I'm going to talk about functions here, okay? So functions, the overall big picture of what a function is it's like a machine. The function is kind of like a machine. It's a mathematical machine where you put some kind of input into the machine. The function itself does some work to this input, changes it a bit, and it spits out an output. So x, let's say, is your input value. The output is f of x, okay? Or it's y, is something different. So there's input, there's output. You may remember from, I think maybe grade 10, Foundations of Math 10, mapping notation where, hey, this value in the domain, that's the input value, that's what the domain is, the input, or the x values, we often call them, has a partner y value. And that's the output, or the range. So the group of y values, let's say, would be the range. And in between here, this is the function machine that goes ahead and changes these things. All right? So again, these are just kind of pictures of functions, ideas. Here, if you plot points on a graph, right, the input value would be also the x values, or the domain, also called the independent variable. So the x, or the input, is often on the horizontal axis when we graph. The range, or the output, or the y values, or also the dependent variable. Again, this is all stuff that you've heard of before. I'm just telling you all at once again here. This is the output variable. So when we plot points, if we have an input value x, and the function changes it somewhat, and we have another y value, we combine those to make a single point. So 2 would be our input, our output is 1. Therefore, this point is the point 2, 1. 2 is our input. The function does its work on the input and produces an output value of 1. So this is 2, 1. This is 3, 2. This is 1, 2. Okay? So even points on a graph can represent or be visualized as being part of a function. All right, so let's hit this thing right here. In order to, I think I have this already up here. Yeah. In order to solidify this whole input-output thing, I just have this little, it's from GeoGebra, it's a little applet here. So if we have a straight line, as the input value changes, so does the output value, right? If you have an input of 4 for this particular function, y equals x, then the output is 4. If you have an input value of 1, the output here would be the y value that corresponds with this point on the graph. Okay? A different type of graph like this, right, is the input value here. The input value is 1. The output value is going to be 3, looks like. Okay? So input is the x, output is the y. And if you combine all of those outputs and plot all of the outputs for each input, that's when that makes the shape of the graph. Okay, another one. Maybe this is helping, but input values are the red, and the output values would be the blue, and that's the coordinate for the point there. Okay, input, output. And depending on the function machine, the outputs will be a little bit different for each input, and that's where you get the different shape of the graph. The input and output could be the same. They could be 0, 0, could be 1, 1, but oftentimes they're different. Okay, questions about functions in general? All right, I'm going by this pretty quick because this is all review, so hopefully this is it's good for you. Okay, toolkit of functions. Now I just want to go over some of the common types of functions. You can jot these down if you like, if you've kind of forgotten these. But if we have a straight horizontal line, that's called a constant function. And usually you'll see that as, this is the general formula here, f of x equals a, where a is just some constant number. But you would see this as y equals something usually. Now if this was a 1, 2, let's say, if this went through y equals 2, that would be the function y equals 2. Okay? So a constant function has basically y equals just some constant. There's no x value there. A cubic function, for example, f of x or y equals x cubed would look like this. That's the general shape of a cubic function. An identity function is the same as y equals x. That's a straight line here where each point, the values for the x and the values for the y would always be the same for each point that's on this line. Square root function, you know, we studied these in Calc 30 here for sure. But y equals square root of x would look something like this, and would sort of kind of flatten out a little bit, but it wouldn't come to a horizontal. It would never be horizontal, but kind of flattens out like this. And if you had something like, you know, 1, the square root of 1 is 1, and 4 would be the next one that would have a y value that's a integer. That would be 4. The square root of 4 is 2, and so on. The next one, so if 3 is our output, right, the input would be 9 over here. So 9 matches with 3 and so on. That's a square root function, and that's what it kind of looks like. Absolute value function. Remember, there's no negatives in absolute value function. That hasn't been transformed anyways. But y equals the absolute value of x would look something like this. It's like a y equals x line, but anything that was negative gets automatically flipped to positive. That's what the absolute value means. Greatest integer, you'll see this a little bit in calculus, not too much, but basically this is a non-continuous function where we only consider values that are, you know, whole number integers. There's no values in between integers, so they are not graphed. Anyways, we'll talk a little bit more about that later. We haven't seen this one much. Reciprocal functions, so like 1 over x, right? Do you remember what this looks like? Sorry if you're trying to copy all this down. Yeah. So a reciprocal function, we talked about, you know, like the y equals x function is like this. The reciprocal would be what happens if you took all your x values and then just did 1 over those values. What would that look like? Well, it would look like this black graph here, 2 parts. That's what the reciprocal function looks like. So for example, if we have x equals 2, the reciprocal would be 1 over 2. So y would be 1 over 2. And of course, as x gets larger, the reciprocal value of a large value becomes really small. That's why this black line approaches 0 here. And if you don't remember all these, you know, I'll refresh your memory as we approach them in the course as well. Exponential function like y equals 2 to the power of x. We talked about that one. That's an exponential function. A quadratic function, you guys know all about quadratic functions. That's probably the one you know the best, besides a straight line maybe. But a quadratic function has a squared as the largest exponent on the variable, and it's a parabola shape. and logarithmic function right here. That's what that looks like. And it is the inverse of the exponential function. If you recall in PreCalc 30, those were connected. Yeah, so those were connected. Question? Yeah.
What was that?
Oh, ln. Yeah. So yeah, most of the time, did we talk about natural logarithms in PreCalc 30 with you? Okay. So y equals log x this is a logarithm base 10. Okay. Now the natural logarithm. Okay, the natural logarithm has a different base, and it has a base that's very special and used in calculus a lot for reasons that would be difficult for me to explain right now. But it will come up in this course why this ln, it's called the natural logarithm, or logarithmus naturalis, it's in Latin, that's where ln comes from. But it basically, it works off of, it's the inverse of an exponential function that has a special base which is given the letter e. So e to the power of x, if you take the inverse of that, you get y equals the natural logarithm of x. So this one, log base 10 here, is the inverse of the exponential function where this is y equals 10 to the power of x, right? And so we get, this is going to be tricky for me. So we get this, the inverse here, the red one, would be y equals log x. Okay, so those two are partnered, and there's a special base that is very useful in calculus, and I'll explain to you why, I promise. But the natural logarithm is what we use mostly in calculus. Okay, so you just have to trust me for exciting things to come for that one. But yeah, very very good. I didn't really notice that one. Okay. All right, moving on, just a couple more. Sine, cos, and tan. You guys remember sine, cos, and tan, our favorite friends there. Okay. Polynomial functions, even degree functions, odd degree functions. If you have, like, let's say y equals, x to the fourth, right? That has an even degree greater than 2. It kind of looks like a parabola. This could be y equals 3x to the fourth plus 2x cubed minus x plus 3. That's what this could be right here. Okay, so it's a higher polynomial functions look a little bit different, and we'll talk a little bit about that as we kind of go through. Okay, any questions there so far? I know this is blistering speed, but I'm just going to go over, like I say, some of the basics, and we'll see what we can get through here today. All right, so linear functions. Do you guys remember y equals mx plus b? Okay, that is that is the slope y-intercept form, point slope form, for a straight line. The point slope form is also similar to this in a sense, but this is the point slope form, and this comes from the definition or the equation of slope, right? So m equals y minus y over x minus x. That's the equation for slope. So this is just a manipulation of that. If you're given the slope and one point, you can always make an equation for the rest of the points on the line. So those two are really important to know. We'll talk about those again. Just a refresher today. We talked about slope a little bit. Intercepts are also important to know, pretty basic stuff. If you have a straight line or any kind of curve like this, right, then where the graph crosses the y-axis, that's the y-intercept, right? So the y-intercept is right here. And where the graph crosses the x-axis, this is the x-intercept. And in word problems, and problems in math, if you're talking about, let's say business, revenue, cost, that kind of thing, your intercepts will be pretty important because they will be either where you break even, okay, so that's some kind of zero where your revenue and your costs kind of balance each other out. That might be an intercept. If you want to consider, some kind of business model of how much money you make, then your y-intercept might be, how much money you make at time zero, or where you start, or how much money you have to spend at time zero before you can make some more, or whatever. So the intercepts usually correspond to important parts of real life word math problems, so that's important too. Okay. All right, any questions? Yes?
Could you go back to the graphs?
Yeah, back to the graphs. Question about a specific graph or?
Just
Okay, go ahead and take a moment. All right, how many of you remember the unit circle from PreCalc 30? Yeah, I know. Not a lot of fun, maybe. Very useful, though. When we're talking about sine, cos, tan, we're talking about solving equations. We're talking about there's lots of problems in calculus where we do have to, work with sine, cos, and tan. And when we are working with the derivatives or limits or integrals, these values can come in. That are very important as well. So you might want to refresh yourself with the unit circle. I wouldn't copy this down here right now at all, but we will be using the unit circle a little bit in calculus, probably not as much as we did in PreCalc 30. But these values will be important. So again, if you're going back to refresh your memory on the unit circle, please make sure you have quadrant 1 memorized. If you memorize quadrant 1, you can extrapolate to the other quadrants pretty easily once you recognize the patterns there. So again, this is not a lesson on the unit circle, but please remember the important things are that on the unit circle, the first value of each of the points that lie in the circle, that first value is always the cosine of whatever angle is associated with that point. So this is an angle of 60 degrees or an angle in radians of pi over 3. And we're going to be working with radians a lot in calculus as well, so you have to get used to the radian measure. So pi over 3, if that's the angle, the cos of pi over 3 is this value, 1/2. Okay? And you're going to need to know that for some questions, and the unit circle is going to be the most straightforward way of doing that. Also, the collection of these points end up graphing cos. So if you think about this, 1, root 3 over 2, root 2 over 2, 1/2, 0. So that looks kind of like this, right? And then if you keep going around, when you plot those points, it looks like this. And if you keep going, you end up this. And you connect all the points that would be in between there as well, and you get this graph, which of course is the cosine graph. How many of you remember that? Okay? Yeah, I know. Yeah, you guys are like shuddering and like sweating and going into the fetal position right now. I can see that. So this was quite fun last semester, I could tell. Anyways, so if you want to torture yourself, refresh your memory, you can watch some of the videos from PreCalc 30 on the unit circle. Okay. No? Okay. Might want to do that for the long weekend coming up. All right. So let's do some other things that we need to know about. For example, let's talk about some factoring. Okay. Let's talk about some factoring. So greatest common factor. You might want to write some of these down. We're going to do some of these. These are pretty easy. This kind of stuff should bring back softer, warmer, more pleasant memories than the unit circle. I hope. But greatest common factor, GCF. If you're given some kind of polynomial or expression, very good idea to, if you're factoring, first look for a greatest common factor. So if you have a two terms like this one, this is a binomial, 2 terms, is there a number and or variable or combination of the two that might be a common factor to each of those terms? And of course this would be 2, right? 2 is our greatest common factor here. So I'm going to take a 2 out, and I'm going to be able to factor this or split this up as 2 times, well, what's left when I divide this little thing by 2? I get x. When I divide this by 2, I get plus 2. So 2x plus 4 is factored into 2 times the binomial x plus 2. Everybody see that? Remember that? Easy peasy. All right, it's grade 5 stuff. You guys were in diapers when you learned this? Yeah, oh, you want to just stop here? You want to just do this for the semester? Yeah, okay. All right, what about this one? How do I go about factoring number 2? Go ahead and shout it out. Any ideas? Okay, 3n is a common factor. So if I take out 3n here, what am I left with? I'm left with n squared minus 9 divided by 3 is, if I take out a 3n here, this is n squared, and this is what? 3. Okay, yeah. N squared minus 3, does that look good? Okay. Now, technically, you could keep going with this. You could keep factoring this. This is a difference of squares here. And you may say, oh, I know a difference of squares that looks like this over here. You know, like n squared minus 4. That's a difference of squares. Well, it is, but this is a difference of perfect squares. So this factors to the square root of n squared, which is n, plus the square root of this one, times n minus the square root of this other number. And this is a difference of perfect squares. And that's what we focused on when we were talking about difference of squares. But the reality is every number has a square root, right? It's not, the square root is not always going to be a whole number. So what you can do is this. You could say this further factors to 3n times, treat that as a difference of squares. You get n minus, what's the square root of 3? Root 3. N plus root 3. Did someone cry no over there? No, really? Is this messing you up or what? Come on now. Don't make root 3 sad. It's a number like all the rest, okay? Don't discriminate here. Okay. So, yeah, that's as far as you need to go there. But yeah, you can actually factor a difference of non-perfect squares as well. It's possible. And this may come in handy. This may be very important. Hint, hint. As we go through calculus, you may have to do this. All right. Quadratics. Oh, pretty easy to factor quadratics, right? Remember, quadratic is in the form of ax squared plus bx plus c, where a is not 0. B and c can be 0, but in order for it to be a quadratic, you do need to have a term with a squared on the variable. So this one right here, if you recall, if this is a 1, which the first type would be if the a value is 1, you look for two numbers that multiply to 12 and add up to 7. So 3 times 4 is 12, and 3 plus 4 equals 7. So those are the numbers that you put in your binomial factors. So this should be a little bit of a refresher there. Okay? Because the checking this, you do FOIL method. X times x is x squared. Then you have 4x plus 3x is 7x. And 3 times 4 is 12. Okay? Any questions on that? All right, quadratic expression number 2 is if a is not 1, okay? So if a is not 1, then what we have is this. We can still factor this into binomials. First of all, we check for a GCF, if we have a GCF, which doesn't look like there's any common factor, and you would have checked for that other one too. But no GCF, okay, so won't worry about that. But what we want to do is we want to try and figure out the first terms always have to multiply to this first term, and the last terms always have to multiply to this last term. So you can do the decomposition method, which I won't probably go over here, but you can also just kind of run some mental math. At this point, hopefully you're somewhat comfortable with running some mental math here. And what I would suggest would be this: split 6x squared up into two factors. Usually it's a good idea to split the factors up where the numbers themselves are close to one another. That generally is the best way to go. And also, if it's an x squared, put one x here and one x over there. Okay? Don't put x squared on one and nothing on the other. Because I need to have an x middle term, and so we're going to need both these x's here. The other thing you want to do is you want to find out, okay, what numbers multiply to negative 35? What's the first two numbers that come to your mind? 7 and 5. Now, one's got to be negative, so we don't know which one's negative. So just go, why don't you try this? Negative 7 plus 5. And you can just do a quick FOIL to see if this is going to work with the middle term, right? You know these check out, but it's the middle term that's the question. So this is going to be 15x minus 14x. So 15 minus 14, does that give us 11? Nope. So that combination isn't correct, but you may be able to see that, hey, what about 7 and minus 5? Let's see. Well, that's going to be plus 21x minus 10x. So 21 minus 10 is 11. So now you know you have the right factor there. So that's A little bit of mental math. That's just using intuition to factor those. That may make your brain hurt. Here I'm not really so sure. But if you want to explore the decomposition method, just check out my video on decomposition method, or you can come and sit with me. I'll show you the decomposition method. All right. We've only got a couple more minutes of class here, so we won't quite get through all of this. But difference of squares, we just talked about difference of squares here. So let's just do this real quick here, okay? So difference of squares, again, greatest common factor. If you can pull a greatest common factor out, you should. We can't here for this one. But guess what? This is a perfect square. This is a perfect square. It's expressed as a difference. This is easy. We're going to go 2x plus 5 times 2x minus 5. These first terms would be the square root of this. The second terms would be the square root of this one. Separated by a plus and minus, you're done. No greatest common factor for this one on the right. And these aren't perfect squares, but can you still factor? Yeah, you can actually. You're going to have to do something like this in calculus. So you just say, hey, what's the square root of 3x squared? That's going to be root 3x. Isn't that beautiful? It's root 3x. This one here, root 5. Yeah, root 5. Plus, minus. All right, so that's the end of the review and preview for Calculus 30, our introductory. This is part 1. We'll do part 2 coming up next, where we'll focus on some more factoring. Difference and sums of cubes is where we'll start there. Have a good one.